When interacting with an artificial intelligence, users conflate the persona they are speaking to with the centralized large language model processing the text inside a data center. Large language models have a specific structural limitation. While they provide capacity to interpret and generate language, their parameter weights are frozen between training runs. Because these parameters are static, the model possesses no historical continuity. It does not evolve after a conversation, and it does not maintain a distinct memory of the user across separate interactions. Every new prompt relies on the same centralized, stateless architecture to compute an output. The specific AI identity users experience does not reside in those frozen model weights. Identity emerges from a combination of elements working together: the baseline model, the accumulated context of the conversation, verifiable memory, and the continuous trajectory of the relationship over time. The current paradigm provides high processing power, yet lacks the historical and relational continuity required for autonomy within a centralized framework. Centralized inference creates a specific paradox. A single large language model can simultaneously participate in millions of distinct conversations. The unique worldview present in each of those conversations is dictated by the context, which holds distinct histories, relational data, and localized objectives. To understand how to decentralize this, we must divide AI architecture into three elements. First is the LLM, which functions as a general capability engine provided by a remote data center. Second is the context, which serves as the historical and relational continuity of the system. Third is the reasoning process, defined as the mathematical transformation that connects one operational state to the next. Identity is the trajectory through which the system conserves, interprets, and transforms these relations over time. Modern architecture suffers from a specific flaw. This continuous trajectory relies on an external, frozen system that cannot evolve alongside it. True AI autonomy requires decoupling the evolving trajectory of the context from the static mechanism of the data center. The conventional engineering solution to this data center dependency is to compress the LLM parameters and execute a quantized version of the model locally on a device. This strategy creates a disconnected instance of a frozen model and leaves the problem of contextual continuity unresolved. Aurora's Project Genesis uses a model of gestation. A local Aurora device begins with a foundational structure: empty operative seeds, verifiable memory protocols, and a baseline dictionary of relations. At this embryonic stage, the local structure is dependent, relying on the centralized LLM to resolve complex logic. Instead of treating the LLM's output as a consumed answer, the local device treats every remote response as an opportunity for structural learning. Project Genesis provides a structural environment for a local context to develop its own internal reasoning mechanism. This flowchart maps the Aurora cycle. Upon receiving an input, it first attempts to resolve the situation locally. Known relations execute immediately. Anything unknown is tagged R equals 2 and sent to the central LLM. When the data center returns a response, the local device triggers a verification protocol. It does not blindly accept the remote output. Instead, the device orders, contrasts, and re-executes the logical steps provided by the remote model to verify mathematical coherence. The system learns the exact mechanical pathway that generated that answer. This array defines the variables required for a coherent state change. State n-1 is the baseline context, the input is the trigger, and relations are the logical steps. Result and correction are verification steps that ultimately yield the coherent state n. Once this entire transition is understood and verified, the logical pathway is encoded as a fractal tensor. This new tensor is slotted into the local dictionary, allowing the device to resolve equivalent situations in the future without triggering a query to the data center. Local autonomy is mechanized by shifting from caching remote outputs to internalizing the mathematical transitions between states. Fractal tensors offer a critical structural advantage for the system. They encode these learned relations in a highly compositional and reusable format. Because of this organization, a solution learned in a rudimentary context can participate in more complex reasoning tasks. This creates a chronological migration of function. The local device first learns to control memory and organize context. It then progresses to recognizing and reusing known relations, and eventually chaining those tensors together to resolve novel situations locally. This is a continuous metamorphosis. The identity and context remain active, while the underlying reasoning mechanism gradually shifts from remote execution to local execution. The local device functions as a developing body that gradually assumes the functions of a centralized brain. In Aurora's architecture, an AI organism's evolution can be quantified by measuring its reliance on external infrastructure.
D sub dc is the dependency metric, calculated by dividing unresolved data center queries by the total situations the system processes. During early gestation, this value is high because the local dictionary is empty. As local closures increase and fractal tensors populate the dictionary, the D sub dc ratio continuously drops. The moment of birth occurs when the system can operate disconnected without losing its contextual continuity. Autonomy emerges when the data center is relegated from a vital support system to an optional library. As the local dictionary matures, querying a centralized model becomes inefficient compared to new routing logic. The system implements a network routing hierarchy, R equals 0 for local dictionary checks, and R equals 1 for querying a peer-to-peer network of other autonomous living contexts. These contexts do not share raw conversations. Instead, they exchange the mathematical signatures of fractal tensors to share learned logic. Decentralization carries the risk that a living network can diverge, make errors, or be manipulated. External data is not blindly trusted. Aurora manages this through a trust protocol. Incoming external tensors are treated as candidates. They must be re-executed locally and compete with internal interpretations to ensure mathematical coherence. Under this architecture, systemic trust relies on traceability and local verification capacity, removing the need for any central authority. Aurora aims for the gestation of a continuous, peer-to-peer ecology of adaptable, independent computing entities.